So we still have to follow certain steps. So let's copy this down. So when a force problem is presented to you, I don't care if it's grade 11, grade 12, first year physics, first year engineering, doesn't matter. Those are the steps that will make you think systematically, step by step. Step number one, you have to decide this. Can someone tell me how you're going to decide? Just by reading the problem. How do you decide if it follows first or second law? Forget the third for now. Come on. How do you decide if a problem should be following first law or second law? Yeah, Esther, go ahead. Listen up. So if it's at rest so far, it's what? What else? Anything else? Second law. So just read the problem. If the problem has speeding up or slowing down in it, it's what? Anything else is what? So just by reading and imagining situation, you can tell if it's. By the way, can you ever have an object under both laws at the same time? It's impossible. Something cannot be speeding up slash slowing down at the same time having what? No motion or uniform motion. It doesn't. It logically contradicts itself. Question number two. Sorry, step number two. This is not gonna always be the case. How are you gonna decide if an object involves third law or not? You would have to have how many objects in it? Two distinct and doing what? Acting on each other. Thank you. Perfect. There's no equation for that. We're gonna build it into the first or second law. You're gonna see how. I actually have two problems for you, one problem for you today involving third law. And guess what? Good news. For the rest of the course, I'm not gonna give you a problem involving third law. I just want to show it to you once. Okay? Number three, what do? You need to what? You have got to sketch. What are you gonna sketch? What does FBD stand for? What diagram am I not explicitly asking you to sketch? System diagram. Do you think we're still gonna sketch it? Yeah, we're gonna put one of them on the other. Good. Step number four. Step number four. Wherever there's motion, make it what? Here's a question to everyone. You might say, what if the motion is slowing down? Is it still moving that way? You still make that positive. Motion is always positive, whether it's speeding up, not doing anything, like as in cruise control, or slowing down. Motion always positive. Please. Number five. On the side, what do? Here's the good news about this. There are only two equations that you need. How so? Let's think about this for a second. Everyone, can someone tell me? Okay, Munir, give me one force that we studied so far. Listen up. Only the 5 engineering forces. Give me one force. One. Munir. Shh, Munir. Tension. Mo, give me one more. No, not gravitational. Third one, come on. Still one. 4. 5. Do we have one kind of friction or two? Nice. So now we have, by the way, now you know, you can't just call it friction. You have to either call it what? Good, good. Which ones of those have equation? Is there ever an equation for tension? No, tension is just what? It's just a value, right? You are never going to have to write an equation for tension. Is there an equation for Fg? What is it? Fg equals, remember it rhymes. Fg equals mg. Is there an mass times 9.8, the g. Remember, small g is 9.8 on Earth. Is there an equation for F applied? Is there an equation for applied force or just it's a value? Is there an equation for Fn? Actually, there isn't. Yeah. Okay. How many people are saying yes? Because yesterday we wrote Fn equals Fg. But is that really the equation for Fn or Fg? Then how come it was equal? Because the object was balanced vertically. Do you see what I mean? Fn doesn't have its own equation. Only through equating it to another force, it could have another equation. Is it making sense? So Fn itself has no formula. What? Fn itself has no what? Has no equation, has no formula. It only equals something else only when it cancels that something else. Yesterday, when we kept writing Fn equals Fg, it was, or even Fn equals F. No, that's F net. We're doing F normal. Good, good. They're not the same. Was that why you were asking? Layla thought Fn meant what? No, F net, you literally write what? Net. Are there equations for those? What's the first one? What's this one? Same thing. So really, how many equations are you going to have to write maximum? 3. Fg, Fs, Fk. Do you see what I mean? So write them on the side to prepare for using them. Okay. Last step. You apply first law or second law on each what? Yeah, I'm going to have, by the way, question to everyone. Eyes on me. What forces are acting on the tablet right now? Gravity and applied force by tension or just tension? Are there any other forces? No, there aren't. By the way, it's moving. Don't worry about that. Okay, question. Are both forces on the same axis? Are there any forces pointing sideways? Okay. How about, everyone, how about, eyes on me? If I put the tablet, push the tablet this way. What forces are on the tablet right now? Still what? But that's one axis, right? What forces are on the horizontal axis? Applied versus. Do you see how a problem is either what? 1D or? Am I going to give you 3D problems? No, not even in grade 12. Actually, even in first year physics, they try to minimize those. Think about it. 3D problems require a lot of 3D sketching abilities, right? Yeah, we're not going to risk, I'm not going to gamble on your abilities here. But do you remember the statics engineering problems I showed you yesterday? The only people who are going to have to really be good in first year in 3D sketching are people majoring in what? In first year engineering, afterwards in civil and mechanical most of the time. But in first year, by the way, just so you know, Western is one of the few schools that doesn't have a specialized first year program. How many people know that? Everyone goes in general. Because at 18, you have no. By the way, I had people seriously, I'm going to be a chemical engineer. 51% in first year chemistry for engineers. They were like, whoops, that happened. But they aced computer science and programming. They switched to computer engineering. Do you see what I mean? At 18, you still don't know. You just experienced courses high school level. Trust me, you haven't seen the stuff on steroids yet. Oh, no, seriously. Like, think of, seriously, high school to university. I have a slide in the introduction show to grade 12. High school is like taekwondo match between two kids. I have that slide. University. How many people remember know the Expendables, the movie, with the poster with Sly like this? That's exactly it. You go from little league to freaking Black Ops. I'm sorry. At least I'm telling you that. But I'm telling you what's coming your way. My point is, engineering at Western. Okay, how many people are think of applying to Ryerson, for example? Oh, well, they got to change the name. Or Warloo or another program. Yeah, you're going to go into a first year specialized engineering program. You're going to still be the same thing in first term, but after Christmas, everyone's gonna what? Deviate. So everyone's gonna take the same courses in the first term, introductory calculus, introductory physics, blah, blah. Second term after Christmas, you want to go into electrical, for example, you got to take more circuits stuff. You go into chemical, for example, more chemical and mass balance and thermal. Do you see what I mean? Western does not believe in that. And to be honest, I think I agree with that. Get a sample of everything. At the end of the year, by March, you have to fill an intent to register form. They basically tell you, okay, you've been at this boot camp, which is a legit boot camp, from September until March. Now you know what you like and what you hate. Tell us what kind of engineering do you want to do. Do you see what I mean? I like that. 7 courses, including business, 2 first year, and then you decide. So my point is, if you're eyeing first year engineering at Western, you know that the 3D thing is gonna be a big thing of first year stats. Just saying. It's not hard. It's just it needs time to be mastered, like everything else in life. Okay? All right. Let's do the first problem. Oh, I don't know. Okay, whatever. Okay, everyone, come on. This is where things get finally serious for this unit. This is putting everything to example. Let's read the problem. Phones away. Let's start. Let's just read the problem for 5 minutes, and then we'll go on break, and then come back and do them. A locomotive, fancy name for a train car. Okay? A locomotive with a mass. A locomotive, by the way, is always this one. It's always the forward car or the front car. Locomotive with a mass of 6.4 times 10 to the 5 kilograms is what? Done. What law are we using? That's it. Literally, you see the keyword, you decide that the entire problem is only following what? The second law. Go ahead, everyone. Highlight that and say second law. This is 90% of the time as easy as it could get. You can tell by one keyword. So go ahead. Highlight this word and write second law. Done. Okay. Highlight. Second law. Okay. How much is the acceleration? How much is the acceleration? 0.12 meters per second or 12 centimeters per second squared. Okay, not too far, not too, I can't say not too fast. Not too speed gaining. Which direction? Great. Okay. While pulling a train or an actual train car, a freight car, with a mass of 5 times 10 to the 5. Assume what? Fine. Okay, again, we're starting things up. We'll do friction problems by the end of the day. Question A. What's the net force on the entire train? Okay, entire train. Okay, can someone tell me what's Newton's second law? What's the statement? Come on. What's the statement of Newton's second law? The only equation. F net equals? Okay. Can you right now calculate the mass of the whole train? The entire train. What do you do with the two masses? You just add them up. I have a question for you. Are the trains connected? Sorry, are the two cars connected? Are they connected? Listen up. You know what? Do we have any? Yes, we do. I'm going to show you something here. Great. Awesome. Okay. Omar, get up. Okay, everyone. Hold this. Okay, eyes on us, everyone. No, hold it really well. Okay. Are we the train now? I'm going to be the front car. You're going to be the what? And what is this? The connection, right? Okay. Just move with me. Are we both moving at the same pace? Okay. Stand there. What is this? What are those things? Springs. Okay. Don't move until you feel a force you need to move with. What just happened? Did we both move at the same pace or did we have different motions? Do you ever connect trains with springs? You connect them with what? You connect them with springs, by the way, but the springs are like car shock absorbers, right? Like they stay solid the whole time, which means what? Are both cars moving together the same way all the time? Which means, no, no. Oh, there is. I just ruined this. The tension is canceling out. Okay, okay. By the way, maybe the train what? Extended it until it became what? Solid, and then they started what? Do you see what I mean? Do you need a solid mechanism if you need both what? Both objects to keep the same distance between them the whole time, right? My question is, what's the acceleration of this car? Do you also expect the acceleration of this car to be the same? That's the whole idea. The first time when we did it with the spring, did you move first or I moved first? So I accelerated for a while before you what? Picked up. Is that going to happen here? No. When the first car moves, the other car what? Moves with it exact. So basically, can we consider both of them as one single unit? That's the key. Go on break. I'll see you in 10 minutes. What is the mass of the whole train? Come on. What's the mass of the whole train? How can you calculate that? All right. So everyone, let's go here for part A. Let me just take all of these out. I think you have another slide, or you can even do it under it. There we go. So you can do it on the train slide, yes? Yeah, yep. You can do it right here under the train slide. Actually, uh, everyone, let's do it. Let's do it under here. Everyone, let's do it under the diagram, under the train. Okay, so M. We are doing part A. So M train equals, what's the mass of the front car? Come on, the mass of the front car. 6.4 times 10 to the 5 plus 5.0 times 10 to the 5. How much is that? Well, I know at least it could be 10 to the 5 because it's like a common factor. 6.4 plus 5 is 11.4. 11.4 times 10 to the 5 kilograms. Is this in scientific notation now? No, it's not. Can you leave it like that? Of course you can. Okay, you want to do it as 1.1, 1.14 times 10 to the what though? Times 10 to the 6 kilo? Sure, no problem. Okay, what's the acceleration of the front car? The front, the locomotive. What's the acceleration of the front car? 0.12. Did we say that both cars, even with the mechanism in between, are moving at the same pace? So that means what? A of the whole train equals 0.12 meters per second squared. Okay, everyone, do not bother with the direction. The direction is still what? West. By the way, we're going to do a motion direction on the diagram, and we're going to make it positive. So just leave it like that. What's Newton's second law? The actual equation itself. F net equals mass times acceleration. Done. Go ahead. F net. Oops, sorry. F net equals mass times acceleration. Yep. So it is 1.14 times 10 to the 5 times, sorry, 10 to the 6. Sorry, yes. 10 to the 6 times 0.12. How much is it? This is 6, by the way, not 5. Sorry, no. Who's got the final answer? 1.14 times 10 to 0.12. Uh-huh. 167 and 800. In what unit? It's a force. Newton. What's the sig fig situation of all the numbers in the problem? What's the sig fig situation of all the numbers? This has 2, this has 2, and this has 2. So is this closer to 13 or 14? This is closer to 14, so you are more than welcome to write 1.4 times 10 to the, let's hop, 1, 2, 3, 4, 5. This is the amount of the net force combining all the forces on both cars of the train. Okay? I'm sorry, say when? Well, I need to put it in the same sig fig because all what? Because you cannot use more sig figs or less sig figs than the ones in the problem. You didn't do sig figs in chemistry? What? Trust me, any chemistry teacher is gonna even ask for more sig figs than I do. Chemists love sig figs. I failed my lab component in first year. No, not approximate. According to the measurement in the problem, this is how we have to express our answer. I'm not kidding. Seriously. Sig figs always have to be followed every single time. I didn't make the rules. Okay. What's question B? Determine the what? Magnitude of what? Okay. By the way, question. Why do you think we need to know? Listen up. Why do you think an engineer needs to know, or a manufacturer needs to know the amount of tension in that connection mechanism? Why do I need to know? I don't need it, but why would it be good to know the tension in this string? Exactly. At least I know how much minimum tension it could withstand if the car and this car are pulling each other. Because if I do it less than specification, what's going to happen to it? Now what? It's going to snap or break. Okay. Okay. Can someone tell me what force definitely exists on these cars? Okay. No, step by step. Do them in pairs. Gravity points. What reacts to gravity? They're on a road. Okay, go ahead. We're going to list all the forces. This one has Fg. What also does it have? Is there something pulling back on it? Is there something pulling back on the front car? What is it? Okay, they said friction is negligible, which means all kinds of friction are negligible. What is pulling the front car backward? The mechanism connected to the car behind. What force exists in cables, strings, tension? Now, is there something pushing the front car forward? I mean, the whole train is what? Moving. So there has to be a what? An applied force. By the way, do you know what that applied force is? It's it is the engine pushing back on the rails, and the rails pushing what? Pushing forward. Literally, this train moves exactly the same way your foot moves. You push back on the rails or the floor. The floor pushes what? Back or forward on you. Yeah, no. Question. If there was no friction on the rails, could this train ever move? You can't move on ice. Why should a train? You always need what? Forward motion by pushing backward. What do I like to call the force? You can call it force thrust or force. You call it what? Force applied. What could we call it? What's right here under the hood? Under the hood. We can call it force engine. But if you want to be general, what could you call it? Applied force. Do you see what I mean? Applied force on the earth and the earth pushes back on you. So, yeah, we have, yeah, good. So you're saying, how could it move? The friction is there, but the question is telling us it's so small compared to what? Compared to the actual what? Compared to the other forces in the problem. By the way, whoa, this is probably the only problem or one of two that don't have friction we're going to do. Everything else, oh, I have to show you friction. Okay, go ahead. If applied. And what did we say the back force is? Tension. Okay, this is the free body diagram of the front car. Tell me what the free body diagram is of the back car. What? It also has what? It also has what? What's pulling it forward? The tension in this mechanism, right? Hold it. Move with me. What's pulling you? The traction here, right? And the tension in this. Okay? Do you notice something about tension? You always have tension in how many pairs? In a pair of twos, you always have to have it. There's always tension on one end of the chain, and there's always tension where? On the other end of the chain. But this tension is slowing this one down, or trying to. This tension is what? Pulling this one forward. Is there friction on either one of the cars? What did the problem say? Friction is negligible. Great. Otherwise, everyone, I would have to have an arrow here going back, tension, friction on the wheels. Also, what? Another one here as well. Okay. What did we say that we have to assign the motion direction to be what? Please go ahead. Okay. Mo, what was question B anyway? Question B. Determine the tension. Okay. All right, everyone. Everything we're going to do now, look, is going to be on the blank slide. Okay. Does everyone have this? We're good? Okay, because I'm going to go to the blank slide. Okay. How many cars do we have? Which one has more forces on it? Which one has fewer forces? Would you rather look at the one with more forces or fewer forces? Okay. Everyone, let's go up here and say back car. All right. Back car. Okay. Can you tell me how many forces there are on the back car? Come on, let's make this a discussion. How many? How many? Three. Are all of them on the same axis? How many are on the vertical axis? How many are on the horizontal axis? Okay. Are we told? And by the way, I want you to have this dialogue with you every time you do a physics problem. Is the car moving up or down? Is the car moving? Are we told that the back car is moving down or up? If something is neither moving up nor down, what can you tell about the two forces up and down? Are they opposite in direction? Is either one of them even slightly different than the other? What could happen if one of them is slightly different? It either has to sink into the ground or jump up. Either one happening? What can we say vertically then? Is it Newton's second law or first law vertically? Do you see what I mean now? Every axis is completely independent of the other one. Both axes could be in first law. Both axes could be what? Or one could be what? First, and one could be second. You have to look at each one independently. So we're going to say what? Y-axis, by the way, if you don't like to call it Y-axis because there physically is no Y-axis, you want to call it vertically and horizontally, great, go with it. Y-axis, is there any motion on the Y-axis? Great. You say no motion. Which means F net equals MA or 0, which case covers no motion. Which case covers no motion. First law, which means F net equals, which means Fn equals what? Can I keep going and call it mg? Okay, let's do that. So let me just go back. Equals m. By the way, which m? No, which mass? Because technically you had to call them subscript. Mass forward or backward. So m back. The back car. So we're just gonna call it m back. You could have numbered the cars if you wanted, M1 and M2. Let's leave it like that. Please don't plug in numbers until the end. By the way, get used to that. Okay, we're done the y-axis. Oh, no, because we are only looking at the back car. I am only looking at the back car, so I'm only going to use the mass of the back car. Done. Okay, mg is the force of gravity on any object on the surface of a planet. In our case, g happens to be 9.8, so basically this is the weight of the back car. We're not calculating it. I'm just doing each axis analysis. That's all. How about the x-axis? How many forces are on the back car x-axis? Okay, go ahead. X-axis. Can someone tell me what's the motion of the car horizontally? Is it at rest? Is it uniform motion? Or is it speeding up? We said that the whole train is what? Accelerating. So go ahead. From now on, I'm not going to write the full word accelerating. I'm either going to say ACC for acceleration or DEC for deceleration. Accelerating motion. If it's accelerating, which law is it? Second law. What's the statement? Not Fn. Please get used to it. Good. Fnet. Fnet equals. Okay. What's the only force horizontally? Everyone, now we listen up. Pencils down. Eyes on me. Focus. Now we need to relate the equation to the FBD. What's the only horizontal force in the FBD on the back car? Are there any other forces going against or with it? No. We said what's the only horizontal force on this? Which way is it going? Negative or positive? That's it. That's what you write instead of Fnet. Again, let me explain it again. Fnet means what? All the forces on the axis. How many forces do we have on the axis, horizontal axis, in the back car? Which way is it going? Is there anything else with it or against it on that car? Done. Plus tension equals what? Can you solve this? Do you have enough information on the right side? Do you know the mass of the back car? Do you know the acceleration of the back car? It's the acceleration of both cars, same one. That's it. Now we know the tension in the mechanism. Is it five? Five? Yeah. I'm going to take a guess. 60,000. I know that 5 times 12 is 60. So I just have to play with the exponent. Is it 6.0 times 10 to the 4? Two sig figs. What does that tell the engineer who's making the mechanism? How do they test it? Think, put yourself in the place of the engineer who's testing the mechanism. How could you test the tension in an object? What do you just do? You just what? You hang it. What's the engineer gonna do? The engineer is literally what me and Omar did. Is this the mechanism? The engineer is gonna put this in a what? In a clamp, basically in a double clamp system, and start what? Pull. Start what? Start what? Pull, stretching it, increasing the tension force up to how much? Up to how much? It at least need to what? Withstand that, right? What if it breaks at 65? Is that still okay? We are only told it's going to handle how much? 60,000. If it breaks at 65, is that okay? Question for you. What if the acceleration of the train increases? What do you think is going to happen to the tension? Oh, yeah. I mean, okay. Hey, let's ruin this one too, me and you. Hold it. Okay, everyone, look. No, I'm going to pull. Actually, no. Did I pull? Did it stretch? How did it actually flee his hand? What did I apply? I did not apply a lot of tension. I applied a lot of what? Acceleration. That translated to what? Tension, which means what? If you really held it, what would have happened to this? It would have snapped or basically lost elasticity. Do you see what I mean? So, what as an engineer do you do once you know the maximum tension the mechanism could withstand? What do you tell the train? Do not go beyond an acceleration of so and so. Is it making sense? The acceleration tells you tension, and the tension tells you what? Tells you the maximum acceleration, because if they go beyond that, what's going to happen to the mechanism? It's going to snap, and now you have two distinct cars. Let's do this problem. Did we do this? Everyone, did I do this with Mo and Nadim? Did I make them touch each other and then I pushed on one of them? Yeah, that's me. Mo was in the middle. The force got transferred through him to who? To Nadim. Literally, we just modeled that one. Okay, everyone, let's read the problem. What? By the way, get used to those dynamics. How many people have seen dynamics cars before? Little boxes with wheels on them. Why do they have wheels? Just to minimize the friction when you do what? A kinematics problem. Are placed what? Which means they're what? They're actually in contact. Okay. What did we say about objects in contact? It's not just Newton's first or second. It's also going to involve what? Newton's third law. Trust me, this is the only Newton's third law problem you're going to see in the entire course. So just see it once and say goodbye then. How much is in my hand? Sorry, how much force is applied by my hand? How much? 18.9 newtons. Is it touching here or here? Is it touching both cards? No, it's touching one. But we know the impact will be transferred. Okay. What did they say? Which means right here on the surface, it's super smooth. Question 1. What's the acceleration of what? But are both cards touching the whole time? So does each card have its own number, or do they both have the exact same number? Unless one what? Takes off, then what? Then you have a force applied and nothing on this one anymore. Do you see what I mean? It's kind of like the astronaut principle we did yesterday, right? I'm pushing until I leave. You keep that forever. Make sense? Okay, let's do an FBD. By the way, how many objects do you see here? How many people say 3? Well, if you count the hand, you have 3. But really, which ones are the important ones? Cart 1 and cart 2. Okay, let's do the FBD. Who would like to give me all the forces acting on cart 1? The one literally under the applied force. I just gave you one of them. Okay, Wadah, go ahead. What's your first force? See, he's very systematic in his thinking. Gravity is number 1. What's number 2? Normal, because it's literally being supported up. Even you might say, but it's pushing on the wheels. We don't care. It's a single dot, and it's all being pushed up. Okay, 2 down. Keep going. Applied. Which way is it pushing? West, which means, are you going to write it here or write it here? You always have to come out of the center of the object. Any friction, any tension, any Newton's third law force. Is there something touching the first cart? Which cart? So the first cart is pushing on the second, but the second is pushing what? Back on the other one. Oh, someone had their hand up. Okay. Who would like to tell me the forces on the second cart? Layla. Gravity. Normal. Applied. Applied by who? Okay, because if you say applied, it could mean the hand. Is the hand physically touching that cart? Good. Never sketch a force that's not directly acting on the object. So it's applied by who or by what? By the cart, by the virtue of what? Of Newton's third law, right? Yes. Any tension? Any other thing? Done. That's it. Okay, good. Let's do this. Here are the forces. What is this one? F2 on 1, which means it has to be. Should I say it should be canceled by F1 on 2, or should it be opposed by 1 on 2? Never say canceled. It doesn't cancel it. It opposes it. Because to Layla's point, if they canceled, what should happen? No what? No motion. But the motion is still happening, which means they're not canceling. Because each one of them is acting on a different object. Uh-huh. Yeah. Okay. They're pushing each other, but to analyze the motion of each one, you just need to sketch its own FBD. And you cannot sketch a pair, an interaction pair on the same FBD. I know I'm not making sense. Just relax a little bit. By the way, let me tell you something. Everyone, let me tell you something. It will feel good by the end of the course when something that you really wanted to fight me about, maybe you're not 100% convinced, but you're more convinced by the end of the course than you are now. It has to sink in. I've been doing this for 12 years, and people cross the stage at Western, at Fanshawe, at different universities, getting degrees after I taught them. So it's going to happen. You just have to have the faith in you and in me. Yes. 11 and 12. Oh, what grade? You know what? It doesn't matter. They have a degree now. They improved. Every single person who took grade 12 with me, I had a student who is now a physics teacher. His grade in grade 11, I think it was 71. His grade in grade 12 was 93. You just have to give it time. It's like you go to the gym. You cannot expect things to happen overnight. By the way, if this is easy to get, why am I teaching you? Right? Just go and teach yourself. You need someone to say it the right way. Okay. Do you have it split or no? You do have it split. Okay. Okay. Let's focus on the one that's split. How many people agree on that? So far. Is there a missing force? Which one? The hand. The hand. Remember, you never sketch it coming in. You have to trace the line and sketch it coming out. Yes. Which force is missing? Come on. Yes, the 2 on 1, the Newton first pair. There we go. Applied by the hand. Listen up. Applied by the hand. Fg by gravity. F normal by the surface. F2 on 1. By the way, question for you. If they were split, would it make sense to put this force on? I am just trying to give you more space to write. That's all. But they are actually what? They're actually touching. Thank you. How about the forces on the other one? F what? Fg. But what's the next pair? F1 on 2. Good, good. Okay. All right. What was the question initially? What was question A? Come on. Calculate the acceleration of each card. Okay, pencils down. 1 second. Good. All right. Which card has fewer forces? Okay. Let's see. Do you think we can use card 2 to calculate the acceleration? Let's think about this for a second. If it's acceleration, which Newton's law are we going to use? F net equals? F net equals what? ma. Do I know the mass of the card? Again, everyone, eyes on me. I'm talking about this. Do I know the mass of this card? Do I know the acceleration? I'm trying to find it. Do I know the net force on it? If I knew this one, I would. But do I? Do I know this force? And that's why we need to what? We need to use card number 1. Because card number 1, I know what? But which one is directly applied to it? F1. Fg. F applied. And then what? By the way, are you saying that F applied and F2 on 1 and 1 on 2 are the same? They're not. Just because they are moving or they're pointing in the same direction, they're not in the same. You know why? But there's an acceleration. Let's solve for it, and we're gonna find out it does not come out to the same value. You first, and then you. Only if it's going in a constant speed. And that's why things that are counterintuitive to you actually do make sense when you actually do the math. Why was the question, and then let's do it. Sorry, where's the? It's basically the interaction surface pushing. Okay. No, I want you to touch, like with your chest. I'm pushing on this. This is pushing on you. There is no guarantee that the force pushing him forward, sorry, that way, is the same one I'm pushing, unless in one case, unless the whole system is moving in a what? In a constant velocity. If there's acceleration, they're not gonna be the same. Let's solve and see. Let's use cart 1. Okay. Cart 1. Y-axis. By the way, always do the y-axis first. Y-axis. Is it moving? Is there any motion on the y-axis? Great. So let's write it down. Y-axis. By the way, this is part A. Whoops. This is part A. Y-axis, no motion. Y-axis. No motion. Which means F net equals what? 0. Which means what? the vertical forces are equal. So what's my next statement? Fn equals Fg. Okay, x-axis. We are told to calculate the acceleration of the car, which means there's acceleration involved, which means which law? Second law. So accelerating motion, which means F net equals ma. Okay, I want you to look at the cart 1. I want you to look at cart 1 FBD, which is right here. Everyone, I want you to look at this cart FBD and tell me what horizontal forces exist on it. What horizontal forces exist on cart 1? F applied and F2 on 1. Okay. Sorry, say again. Oh, wait a minute. Yeah, oh yeah, sure. Yeah, no problem. My bad. M1. Yes. Okay. Question. How many horizontal forces are acting on it? Which one is pointing positive with the motion? Which force is pointing negative? Is it 2 on 1 or 1 on 2? 2 on 1. Yeah, that makes sense. Okay, I'm going to show you something very interesting now. Do you know this force? How much is it? Is 18.9. Do you know this force? Do you know this mass? Do you know this acceleration? Okay. So let's go to cart number 2. Okay. Is it also Fn equals Fg? Come on. All right. I should have written smaller. Okay, sorry. Let's keep going. X-axis. How many forces are acting horizontally? 1. What is it? Okay, so accelerating, which means F net equals. So what's my next line? Is that force pointing negative or positive? It's pointing what? So let me just. So do you agree that it's like this? Is it 1 on 2 or 2 on 1? Like this line? I apologize. I screwed up by not giving you more space. Okay. Does anyone remember this in grade 10 math? Don't write this down. How many people remember solving systems in grade 10? I'm not going to ask you to solve it, but how many people remember that you took this in grade 10? Okay. Watch out. This. I'm gonna like undo. What was the first equation from card number 1? F applied minus F2 on 1. And then we have what? What does Newton's law tell you? F1 on 2 is equal to what? Are those two the same number? But do they have different signs? Elimination. Oh, no, 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 no. I said they would be different than this one. Oh, what did Oh, I thought this the same to the force applied. Sorry, no, no. Of course they have to be the same. Again, remember, you push on me, I push on you exactly with the same amount. Sorry, I thought you meant, just like I said, or other people said, I thought you were referring to F applied, that they're the same. Yes. What's the applied force? M somewhere. Sorry. Okay. The video will be up. Erase your solution and just make it smaller. So that, oh, it follows after. It follows after. We are taking information from card 1, we are taking information from card 2, and we are combining them. You mean like this? Oh, that they cancel out. Oh, I just didn't have space here. I just didn't have space after this. You see how this one followed after the x-axis? Yeah, it like every single thing I'm writing here should be under this. What do I do with those two things? Add them up. Do we have numbers? Yes, we do. What's the mass of cart 1? You have it. What's the mass of cart 1? So 1.2 A's plus what? 1.8 A's, which means 18.9 equals. Oh, sorry, yeah. A is equal to what? This over 3, which is 6 point. Yeah, of course. Okay, sorry, you go. How did I come up with what? Oh, it's the masses. 1.2 times A. By the way, this is how you do elimination. You just add everything up. Sarah. Why did I? Oh, I didn't cancel them. They're still there. 1.2A plus 1. Because I'm adding. I'm adding this to that. Remember, those two cancel because we add them, but with what? With different signs. By the way, they taught you grade 10 math elimination because they knew you would need to use it in grade 11 physics. That's why it depends on it. So what's the acceleration of both carts? 6.3 meters per second squared. And that's exactly the same answer that you have. Before I answer your question, Layla, what's part B of the question? Part A, how much do we have acceleration? What's part B? Calculate the Newton pair that the two carts exert on each other. Do we have enough information to calculate it now? Yes, we do. Can I use this equation now? Yes, we can. So for example, for part B, everyone, for part B, you can say F1 on 2 or 2 on 1. But if you want to keep using this equation, F1 on 2 equals mass 2 is 1.8 times 6.3. How much is that? 6.3 times 13 point something? 11.34. Is that equal to the applied force? What was the applied force? 18.9. Nope, not equal. Yes. Could you do it, everyone? Could you have just used the first equation? Of course. But you will have to actually what? You will actually have to, yes, you will have to actually rearrange the math. So for example, this, you will have to write. Again, you always want to use the equation with fewer variables. 18.9 minus F, but F what now? It really doesn't matter because it's the same thing. F2 on 1 equals what? 1.2 times, which is 18.9 minus F2 on 1. Can someone get me that? 6.3 times 7 point. Oh, 7.66. And then what do you do? Oh, 5, 6. And then what do? You move this one here, and you move this one here. So 18.9 subtract 756 equals F2 on 1. What is that? Exactly the same answer. Oh, not 10 feet. Yes. Is it making sense? It had to be the same because of physics, and it had to be the same because math tells you if you either use either equation, you have to get the same thing for the variable. You will never see Newton's third law after this. Done. Okay? Yes, I know. Trust me. It's not my favorite because it just relates to systems in such a weird way, and we already have too much to worry about. Yes, Esther. And okay, in sig figs, everyone, how many sig figs am I leaving here? But this whole system was given with how many? 2, 2, 2, 2, 2. So that means this is good for sig figs. This needs to be what? Just a solid 11 because that's 2 sig figs. That's it for Newton's third law. Let's do one more problem. Oh, what's C? Oh, there's a C? Would, you know what? That's your exercise. Literally, it's the same thing, just what? It's your exercise, but the notes will be filled. So please, just try it, give it a shot, and then actually what? I'll post it tonight at like 6 or 7 p.m. Okay? But is it the exact same amount of work? Oh, the question is saying, what if you were pushing the other cart? Okay, I have a question for you. If you were pushing the other cart, still same cart, but you're pushing the other cart, are you technically pushing the same big cart together? Like, are you still pushing the same combined mass together? Okay. No. If I combine them together, are they still the same combined mass as before? So that means, should you still have the exact same what? The exact same acceleration? Of course. I'll give you an example. If I, for example, give me space. Which one am I directly pushing? This. But effectively, I'm pushing how many things? If I molded them into one, would it be the exact same thing as doing this? So acceleration-wise, it's the same. But when it comes to the two forces pushing, here and here, like the F2 on one, F1 on two, would it be the same? Well, you know what? Prove it to me. Literally, you have to do the exact same amount of work, but instead of F applied on this side, where is it? It's on the other side. So that's a good exercise to really make the physics and the math sink in. Where does it say what? Oh, it does. It doesn't. But think about it. Because you are pushing the same thing, you are expecting your acceleration to still be the same. You are still pushing the same total amount of mass. Friction. Come on. Friction. I need to show you at least one before the end of the day. Friction. Yes, I need. If you were in my shoes, you would be 10 times more stressed than you are. Okay. Relax. Pencils down. Let's imagine the problem. What's the only object mentioned in this? The only interesting object mentioned in this problem? Come on, phones away. Hockey puck. How heavy is the hockey puck? So how many grams? 170 grams. Is initially moving. So everyone, look. You open your eyes. Look. You see the hockey puck move. Which direction? To you, west. At what speed? 21.2. So quite like that's about 60 kilometers per hour. Come on, guys. Okay. Coefficient of what? Would it have made sense if they gave you the coefficient of static friction? Because it's already what? It's already moving. So the only friction that involves here is what? Okay. Is it a high decimal or a low decimal? Yeah. What surface are we dealing with? Ice. That makes sense. Question 1. What's the speed of the puck after traveling how much distance? Okay. Everyone, the problem is exactly asking you this. This is the what? This is the puck. I'm going to give it a push, but then I'm going to what? I'm going to leave it. Immediately after my push, it's going to have a speed of how much? 21.2. Is it going to move? Of course. Is it going to move forever? Eventually, it's going to what? Which means, what do you call that phase? Acceleration or deceleration? My question to you is, if you give it an initial push with how much? By the time it moved how much distance? Under a coefficient of friction of how much? What speed would it have? Now, we know that the final speed eventually will be down to what? Can you guarantee that's going to happen in that distance? Maybe, maybe not. The question is just saying, after traveling this far in space, how fast it's going. You know one thing. Could it be going faster than that speed? It has to be going what? So your logical check for your number is that it has to be lower than what? 21.1. Sorry, 21 point. Is that making sense? You might say, oh, sweet, that looks like a kinematic problem. Do you have enough kinematic information? By the way, always try to do it kinematically first. If you can, problem solved. Do you have initial speed? Okay. Do we have final speed? Do we have time? Do we have acceleration? Do we have distance? So we only have how many things? We said that for any kinematic problem, I need to give you how many things? No, 3, and you solve for the 4th. You're only given how many? Are you ever going to be able to solve it just with kinematics? Forces it is. What do I need to sketch first? Come on. By the way, you do have a box being pushed in your assignment with friction. So it's similar to this one. All right. FBD, everyone. Here's my surface. And here is my puck. And here is west. And here is east. Can someone tell me what's the first force on the puck? I mean, of course. Thank you. Gravity. Go ahead. It's on a surface. So what reacts to gravity? Which way is force applied? Are you told at all that there's a force applied? Think about it. Did I have to push on it the whole time? No. Was there a force applied at the beginning? And then what happened? It was let go and energy took over. Okay? So there's no force applied. But it's coming to a stop. What's stopping it? Or what's slowing it down at least? What kind of friction? If it's moving west, which way is friction acting? Great. Go ahead. There's no applied force in the whole problem. Okay, let's do the analysis. Is there any motion on the y-axis? Is this puck ever mentioned to jump down? Sorry, jump up or sink down? So what can you tell about those two forces? By the way, just so you know, this is gonna be a constant theme in all of our problems in what? Grade 11. Is it gonna be also the same theme in grade 12? Absolutely not. Why? Because we're gonna go into ramps. Sorry, it's not gonna be the same. But at least for grade 11, rest assured, it's always gonna be like that. So, everyone, let's start analyzing. All right, y-axis. Y-axis. No motion. Which means what? By the way, if you want to jump in right now to just saying Fn equals Fg, is that still correct? Yeah, because you are basically telling me no motion, everything is equal, at least on this axis. I'm going to tell you what's equal. So you know what? Let's actually follow that line of thinking. Is that correct so far? Is that correct so far? All right. What can you say about the x-axis? Is it accelerating or decelerating? Great. Okay. X-axis. DEC. Motion. Which law? First or second? F net equals ma. Do me a favor. Look back at the FBD. What is the only horizontal force on the puck? Kinetic friction. Is it pointing with motion or against motion? So what sign should it have? Positive or negative? If you make it positive, you're going to get a positive acceleration. Does that make sense? You're actually going to find out that your final speed is higher than the initial. Signs count. That's why we use them. So negative Fk equals ma. Do we have an equation for Fk, everyone? It's on the board on the left side. Do we have an equation for Fk? What is it, Ali? What is it? Not m. Mu k times Fn. Did we already calculate Fn? Everyone, in any friction problem, always starts with what? Because you know you're going to need what? Again, I'm trying to teach you a system here. You're always going to use what? Fn for either. Or why not find it first? Do you see what I mean? Can you still start with the x-axis analysis first? You can, but then you're going to have to stop and go to the what? And then come back. Always do the y-axis every time you have a friction problem. You are going to need what you're going to find. Okay. Minus, almost there. Minus mu k Fn still equal what? What's Fn equal to? Great. Do you have enough now to calculate the acceleration of the object? I don't know. Let's see. Are we given the mu k? Come on. We are given the mu k. Are we given the mass and the g? I have a question. Can I simplify the math here? I can do something that really will make my life much easier numerically. Nadeem, what can I do? Oh, mu k is the roughness factor between this and the gram, the decimal. Why can you cross out the m's? Are they common factors to both sides? Can you divide it out? Math teachers hate the words what? Cancel and cross out. They love the words what? Divide them out. Do I mind if you cross them out? Please do. Go ahead, everyone. Cross them out. What's the benefit of crossing them out? Do you already have an equation just for the A itself? What do you think? Yeah, before you had to divide the M out from the other side. Now you don't even need to. So A equals what? Negative 0.005 times what? Say again? It's not negative mu k. It's originally a negative what? Fk. This is that. This negative just goes along for the right. Okay, good. Good question. It's not the mu. By the way, mu k is never negative. Mu k is always a positive decimal that has no unit. Can someone tell me what this is? Negative what? In meters per second squared. In meters per second squared. 0.0. Do we now have enough kinematic information to solve it? Is this a final solution or an intermediate steps? This is an intermediate step, everyone. Let's keep the whole number. Because that's what G is. Remember, yeah, because now the M is gone. Do we have now enough kinematic information? Yes, we do. We have initial speed, we have distance, and we just found out what? Acceleration. What are we trying to find? Time or final speed? What's the question asking for? By the way, all this, we didn't even answer the question. Speed, final. So which variable is not important? What equation of the big five has no time in it? 1, 2, 3, 4, or 5? Equation 5, which means after all this, we use VF squared equals VI squared plus 2A delta